Howdy everyone, and welcome to this webinar on biofabrics, a relatively new and, in my opinion, underappreciated approach to graph drawing, which has the potential to turn your hairball-like node-link diagrams into something much more useful and intelligible. Before starting, I just want to stress that while this talk is being pre-recorded, we will be taking questions in the comments, so if something is unclear or you need more information, just fire away. Before starting, very briefly, my name is Henry. I'm a fresh-faced engineer here at Yworks in Tübingen. And while my background, academically speaking, lies more so in applied statistics and machine learning, I ultimately did my PhD in computer science, specifically in visualization, and more specifically, network visualization. Right, more importantly, what can you actually expect from this talk today? I think you can expect 4 key things. First, we're going to define what a biofabric actually is. Second, we're going to talk about its advantages and limitations so you know when to use them and, importantly, when not to use them. Third, I hope to communicate to you the basics of the layout algorithm underlying biofabrics so that number 4, you can then start your own implementation. We're going to hopefully deliver on these 4 promises by structuring the presentation as follows. First, we're going to talk about the problem that we're trying to solve. That is to say, the issues that exist with node-link diagrammatic representations. We're then going to define what a biofabric even is so we can subsequently discuss their limitations and advantages. With all that in mind, we're then going to talk about implementing one from scratch using our publicly available source code demo as an example. For those watching the video later on YouTube, I just want to point out that you can use the chapters down below to skip ahead to whatever section interests you most. Right, so why are we even here? We're here because we have to address a key limitation that exists with node-link diagrammatic representations. Now, what is a straight line node-link diagram, you might ask? Just in case you need a refresher, it is the most common and arguably the simplest representation of a graph out there. Nodes are represented as labeled shapes, most commonly circles or rectangles, and edges will be represented as straight line segments connecting their source and target node in 2D space. Most commonly, these representations will be laid out using force-directed algorithms such as the Y-file's organic layout. Now, while these representations do well with smaller graphs, as you can see on the right-hand side, as graphs become increasingly large and increasingly dense, they become increasingly difficult to read. As you can see here, as the density of the graph increases, it becomes increasingly difficult to make sense of what we're actually looking at. Now, right now, this assessment of readability in quotation marks is purely vibes-based. We're just looking at 1 or 2 or 3 representations and qualitatively assessing one to be worse or better than the other. But we can do this quantitatively too. For example, we can measure the number of edge crossings that we're dealing with per representation. Here, if two edges are involved in an edge crossing, they're highlighted in gold. And as you can see, the number of gold edges, i.e. the number of edges involved in edge crossings, increases quite dramatically as the density of the graph increases. This makes it more difficult for us to read. The edge crossing number, or the number of edge crossings, is just one of many so-called graph aesthetic criteria. A graph aesthetic criterion aims to objectively, or maybe more specifically, quantitatively measure the readability of a graph. Edge crossings are just one. We could also look at the crossing angle, for example. That is to say, the smallest angle formed by 2 edges that cross one another. We want to maximize this angle as much as possible. Alternatively, we could look at the edge length ratio, which is the ratio in length between the shortest and the longest edge in the drawing. And we want this ratio to be as close to 1 as possible because that means that our edges are all, roughly speaking, the same length. Or we could look at the angular resolution, which is the smallest angle formed by 2 edges incident to the same node. And we want this angle to be as large as possible so that the 2 edges are as differentiable as possible. Now, this is by no means an exhaustive list, right? These are just 4 examples that are easy to comprehend and easy to visualize. But what I want you to take away here is that 1, straight line node-link diagrammatic representations do not scale well with increasingly complex graphs. And 2, we can measure this deterioration in readability objectively or quantitatively using graph aesthetic criteria. Cool. With all that preamble out of the way, I think we can finally ask the question of what a biofabric actually is. To do so, though, we must first answer the question of what a graph even is. Imagine a graph in your head. You're probably thinking of circles connected by straight lines, right? A straight line node-link diagram. That's not what a graph actually looks like, at least not in most cases. A graph doesn't have an intrinsic representation, not in 1D, 2D, or 3D, or higher dimension either. What's important to appreciate is that for a graph to be represented visually, it needs to either be manually drawn or it needs to be laid out by an algorithm, such as the organic layout. Indeed, a graph is just a mathematical description of connectivity, right? This JSON representation on the right is just as valid a representation as the straight line node link diagram. And the straight line node link diagram is powerful. Please don't misunderstand. It's well known and easy to understand and easy to implement, but it's just one possible representation. A circular representation, very popular in the biological sciences, for example, might be the way to go if you need to order your nodes. Similarly, an adjacency matrix might be powerful if you want to avoid edge crossings and you want to order your nodes as well. It's not as well known, and arguably it's harder to learn, but it's just as valid a representation. These three representations are by no means an exhaustive list of what a graph can look like, right? There are infinite possibilities here. But what I would like you to appreciate is that there is no one way to skin a cat. Depending on your users, their expertise, the amount of onboarding you can expect, depending on the tasks you want them to perform, or depending on the message you're trying to convey, a different representation might be the way to go, different than a node link diagram, I mean. And with that, we can finally talk about biofabrics. They are just a tabular representation similar to an adjacency matrix. On the right, you see what the previous graph looks like as a biofabric, right? What's important to appreciate is that even though it comes from the biological sciences, hence the name, that doesn't mean that they can only be used for dynamic biological data. They can be applied to any kinds of graphs, from compound to hypergraph. To understand what a biofabric actually looks like, right, beyond just the sets of lines I just showed you, let's imagine we have a graph with nodes V and edges E. Our nodes will be represented as a series of labeled parallel horizontal lines. So here, for example, node A is our first line, node B our second line, and so on. Our edges will then be represented as labeled parallel vertical line segments connecting their sources and targets. So in this particular case, edge 1, for example, connects nodes A and B. Edge 2 connects A and C. Edge 3 connects B and D. And edge 4 connects C and D. And what I would like you to take away here is that a biofabric is actually very simple. It's just a data table, right? Our rows, our nodes, our columns, our edges. But it belies the power of the representation. By the end of this little talk, this admittedly at first intimidating look at a company network should be far less confusing. Indeed, what a biofabric allows us to do, as I hope to communicate in a moment, is to take complex graphs and represent them in a very orderly fashion that allows us to avoid the kinds of crossings and problems that you might anticipate or that come naturally with node link diagrams. So, now that we know what a biofabric actually is, I think we can start talking about why you want to use one. Before we do that, I think we have to address two key limitations that they bring with them, though. First, they're fairly unconventional representations of graphs. What I mean by that is that where a node link diagram is so commonly used that even lay people can look at them and make sense of them, biofabrics are sort of the complete opposite. Unless you can expect people to learn the representation over the course of perhaps an hour, I don't think you should be using biofabrics in your representation, depending on the expertise level of your users. Moreover, similar to an adjacency matrix, they're somewhat space inefficient. Specifically, they scale at the cardinality of V times the cardinality of E, which depending on the graph's size can get quite large. There are ways around this, but we'll talk about that later. Cool. With those two disadvantages out of the way, you do gain 5 key advantages that are very powerful. First, we can independently order and reorder our nodes and edges. Second, we can independently group our nodes and edges. Third, we can easily include multivariate attribute visualizations for nodes and edges. Third, we can visualize hypergraphs, or maybe more specifically, we can do so fairly straightforwardly. And fifth, they're computationally scalable. We're going to talk about each of them one by one. First, we've already talked about node order, right? And it needs to be said that technically speaking, any representation has a node ordering, right? Even a straight line node link diagram like the one on the left has a node ordering depending on how you project them. But in reality, we don't reason about that order, and we can't change the ordering without changing the entire representation. On the other hand, an adjacency matrix allows us to a priori specify the order that we want and change that ordering interactively without messing up the entirety of the graph. Biofabrics take this a step further. Not only can we order our nodes, we can order our edges. As far as I know, biofabrics are the only representation that allows us to do this, at least in 2D. So, what you see here is the same graph shown 4 times, and all 4 of these orderings are equally valid. What this means is that you could order your edges and your nodes independently of one another according to topology, such as node degree, geometry, such as edge length, or maybe an attribute, such as the height of a user, that is to say, an attribute attached to the nodes. This is incredibly powerful because we can do this a priori and interactively. Moreover, we can now also group our nodes and edges. What I mean by that is actually fairly simple. Imagine we have a simple biofabric like the one we see on screen right now, right? We have nodes A through G, and we have edges 1 through 14. At the moment, we haven't grouped anything. But imagine this represented a social network, right? Where each node represents a person, and each edge a relationship between 2 people. What if people fell into different social circles? Well, in the simplest case, we could just color code the nodes. So node A, for example, falls to the pink social circle, and node C in the blue one. If this was a straight line node-link diagram, this is as far as we could go without embracing a more complex representation. But biofabrics allow us to take this a step further. Because we can independently order everything, we can now order our nodes by their group. What this means is it is a lot easier to now discern which nodes fall into what group, and we can easily see that node group 2 is bigger than node group 1, and we can sort those node groups accordingly. Similarly, if we had multiple types of relationships between different people, right, friends and enemies say, here represented as pink and blue, we can again color code them, but we can again group those edges to make their association to different groups really clear. And because we can sort our groups however we wish, I've here opted to sort them lexicographically. But you could sort them however you want. Now, the reason this is cool is because we can do both at the same time without using color at all, which I think is a big deal, because this is the only representation that allows us to simultaneously show group and edge structure without color, because color is often a reserved channel, or you might want to reserve the channel for something else. And here, you don't have to use color at all to show group structures. Right. Color is often a reserved channel, often when we're dealing with multivariate graphs. What is a multivariate graph? It's basically just an ordinary graph, that is to say a graph that is purely topological, but each edge and node has attributes attached to it. So in a social network, for example, right, each node represents a person, and a person isn't just defined by the fact that they are a node, but they have a name, an occupation, a height, an age, what have you. And those attributes are listed in the node itself, and we want to visualize that information so that the graph analyst, or the user, or the viewer can also make sense of them. So if this was a straight line node-link diagram, we could, for example, visualize node information using popovers. That is to say, you mouse over a node, and as you mouse over the node, a little window pops up next to it that shows all the information that you're interested in, right? In this case, in list form. This is already quite powerful, but it does obscure the geometry of the graph. That is to say that it sits above the visualization, which can make it difficult to make sense of what's happening underneath it. A biofabric is quite powerful in this regard because remember, we have a one-dimensional ordering of edges and nodes, which means that if we want to stack additional visualizations to the left, to the top, to the right, to the bottom of it, we can. So here, for example, you can tell that we have a bar chart on the bottom, and this bar chart's order is the order of the edges above it. And similarly, we have a popsicle plot on the right, and its ordering mirrors the ordering of the nodes to its left. These orderings could influence one another, such that if you reorder one, the other one changes correspondingly. Moreover, because a biofabric is necessarily rectangular in shape, it's a lot easier to include additional windows beside it that showcase all those multivariate attributes that your users might be interested in, as you can see in these small examples here. Cool. Let's move on to something slightly out there, hypergraphs. You may have heard of them, but maybe you don't really know what they are or you need a refresher. They're very simple actually in concept. A hypergraph is just a generalization of an ordinary graph. And an ordinary graph are the kinds of graphs we reason about every day. That is to say, graphs whose edges connect exactly one node and another node, right? So, as you can see in the JSON, for example, we have a source and a target for each edge and nothing more. But while this is enough for many cases, it can also be a limitation. Imagine you're dealing with a collaboration network where you have multiple employees in a company and they can collaborate on projects together. And now imagine that there's a project that involves 5 employees, right? How would you visually represent this? Would you draw as many edges between all your employees as necessary to represent one project? You could, but that's slightly inelegant. And this is where hypergraphs come in. You see, a hypergraph allows for an edge to connect an arbitrary number of nodes. So as you can see in the JSON, for example, an edge is just an unordered list of node IDs. And this list could be empty, but in this particular case, it starts with 2 nodes necessarily and goes all the way up to 4. And what's cool about this is that if we think about this example of the collaboration network again, what this allows us to do is for one project to be visualized as one edge connecting all those employees that are involved. There is a problem though. You see, while hypergraphs are simple in concept, they're very difficult to visualize. What I mean by that is that if we want to visualize them as like a node link diagram, you can see that this turns into a spaghetti plot very quickly. If it weren't for the inclusion of colors, it would be very difficult for us to tell what edges connect what. Similarly, if we use a Venn or Euler diagrammatic representation, it would be equally difficult. Moreover, these kinds of representations are actually very computationally expensive to lay out. But hypergraphs have a bit of a trick up their sleeve here, because we can just include hyperedges by just increasing the number of circles along an edge's line. So here, for example, it's very easy to tell that the 3 colored edges are hyperedges, and we can very easily tell which nodes they connect, and importantly, which ones they don't. I think you'll agree that when we compare these 3 representations side by side, it is the biofabric that is the most intelligible and the most immediately useful. Finally, and perhaps most boringly, I should stress that biofabrics are computationally scalable. What I mean by that is that their layout algorithm is just an ordering of nodes and edges. So as long as your ordering function is reasonably implemented, you won't have any problem scaling biofabrics to large graphs. So, in summary, we can independently order and reorder nodes and edges. We can straightforwardly group nodes and edges. We can easily include multivariate attribute visualizations. We can straightforwardly visualize hypergraphs, and this whole thing is computationally scalable. What more could you want? Awesome. Now that we know what a biofabric is and what its conceptual advantages and limitations are, we can actually talk about implementing one from scratch in Y files. I should stress that we're going to take a look at our source code demo. At the moment, at least, we don't yet have a biofabric layout in the actual core library. Maybe down the line. First, let's think of the following graph as an example. It's a K3 complete graph consisting of 3 nodes and 3 edges. The nodes are labeled A through C, and the edges are labeled 1 through 3. Now, in order to actually load your own data, or this data specifically for now, into our implementation, we expect the data to have a very specific format. First, we expect nodes to be stored in a JSON called nodes, and we expect the edges to be stored in a JSON called links. Each node must have a unique ID field, assumed to be a string or a number, and each edge must have a source and a target. These source and targets refer to the actual IDs of the nodes they connect. So they're also strings or numbers. Additionally, each node can have a label, assumed to be a string, and a group, also assumed to be a string. Similarly, each edge can have the same. Note that with the exception of the node's ID and the edge's source and target, you can rename these fields as you see fit, as we did in the case of the edge's group, which we've renamed to type. Now, if you're interested in simply using our implementation with your own data, you can just make use of the top-level call, which consists of 3 lines of code. First, you create a new graph component, as you would in any case. Then, you instantiate a new biofabric. It is here where you will specify all your optional arguments which dictate what the biofabric will look like. Subsequently, you call the actual layout algorithm, and voila, you have an interactive biofabric ready to go. Now, digging a bit deeper, we can take a look at the apply layout call. The apply layout call does 6 key things. It creates node and edge groups. It sorts those groups. It sorts and then lays out the nodes. It sorts and lays out the edges. It then applies the calculated positions to the actual visual elements on screen, and then it lays out the edge labels. Cool. As we've already discussed in the previous section, and as we've now made pretty apparent in the implementation as well, we need to be able to sort our edges and nodes. And to do so, we need comparators. First, node comparators simply compare and then order the nodes as you want them to. That is to say, you can easily implement your own if you want to, but we've made available 3 basic ones for you to start with. First, degree-based. Degree-based simply sorts the nodes based on their degree in descending order, and then lexicographical ascending and descending, which sorts them based on their label string. Similarly, we've made available 4 edge comparators for you to start with. First, edge length, which is fairly self-explanatory. Lexicographical descending and ascending, similar to the node labels. And then as is, which keeps everything in place. Again, it's very easy to add your own if you want to. But now that we have an ordering of our edges and nodes, we still need to be able to lay them out in 2D space, and for that we have to calculate their coordinates. To do so, we have to know what the smallest space will be between edges and the smallest space will be between nodes. We call these spacings the unit width and the unit height, respectively. The unit height is calculated based on the number of uncollapsed nodes in the drawing and the number of uncollapsed groups in the drawing. This, coupled together with the actual height of the canvas, allows us to calculate the smallest distance that we have to entertain between nodes. Similarly, the unit width is calculated based on the amount of, space we have in the canvas, as well as the number of uncollapsed edges and the number of uncollapsed edge groups in the drawing. I should stress, this was a fairly breakneck look at our implementation, and if you have any questions, which you may very well have, I recommend simply contacting us or maybe me specifically so that we can find a solution that works for you specifically. Right. Now that we have a rough idea of how our source code demo actually works, let's take a look at it and its features in action. More specifically, let's take a look at the aforementioned company network in more detail. To find this demo yourself, navigate to yfiles.com/demos/layout/biofabrics or yfiles.com/demos and look for biofabrics in order to interactively explore this biofabric yourself. All right. Before you, you can see 2 graph layouts. A circular layout on top, and a biofabric below. Both show the exact same network, the company network we discussed earlier, in which each node represents an employee and each edge represents a type of relationship between them. As discussed previously, our nodes, i.e. employees, are arranged as labeled horizontal line segments, and our edges, i.e. relationships, as labeled vertical ones. Our nodes have been ordered by degree, and our edges by their length. This means that, right off the bat, without needing to even interact with the biofabric, we know that the node with the most neighbors is the director, followed by the lead engineer, followed by the senior researcher, and so on. But if you did interact with the network by, for example, hovering over a node or its label, you would be able to highlight the node itself, its incident edges, as well as its adjacent nodes. Similarly, you can highlight an edge by hovering over the edge itself or its label, and you will highlight it together with its incident nodes. You will also notice that the corresponding items will also be highlighted in the above circular representation. The same highlighting also works the other way around, i.e. you can mouse over nodes and edges of the circular representation and see the same highlighting appear in the biofabric below. But if you think back to the image of the company network I showed earlier during the sneak peek, you'll notice that this still looks different. And that's because the screenshot showed this network with node and edge groupings. Well, we can easily add both by simply taking the group nodes and/or group edges boxes. Moreover, you can decide how to sort them by using the drop-down below the tick boxes. Here, you can see the options we discussed previously, i.e. cardinality and lexicographical orderings. Mousing over a group label will show the contents of that group both in the biofabric and the circular representation above. Now, remember how I said earlier that one drawback of biofabrics was their poor visual scalability? Well, there's a way around that. You see, when we have node and edge groups, as we do now, we can easily collapse part of the network that we aren't interested in. This allows us to more effectively use the available 2D space. Moreover, whenever we do deem a particular collapse group relevant after all, we can easily expand it again. However, even with all the node and edge groupings expanded now, the biofabric still doesn't look the same as the screenshot during the sneak peek. The colors are missing. Here, in our source code demo, you can choose between 4 edge coloring modes. None, which is what we've engaged right now. Edge group, which colors edges depending on their edge group membership. Node group, which colors edges depending on their source and target nodes group membership. And node group inverted, which functions like the aforementioned node group mode, but inverts the colors of source and target. And now, with the biofabric colored and grouped, it should look exactly like the sneak peek screenshot we saw earlier. Thank you so much for joining me today. This has been a very quick look at the world of biofabrics, and there's still a lot to be learned and appreciated. But I hope that after this little lecture, this particular biofabric that we showed you earlier is no longer as intimidating or as daunting as it may have been initially. Now, if you want to know more about biofabrics, be it read the original paper, maybe appreciate the design space more, or understand more about the layout algorithm and its constraints, I recommend you check out these 5 papers. With that, my name's been Henry. If you have any questions about biofabrics or the implementation of the source code demo, feel free to email me. Alternatively, check out yfiles.com for more information. And with that, I wish you happy diagramming.